Luciano Castro, who has been at IMPA for a long, long time, if I understand correctly from his biography, except with a gap of several years in the US. I don't know Luciano personally, but I'm looking forward very much to hearing his research in this next talk. So over to you, Luciano.
Hello. Okay, thank you, Jim. Thank you. Yeah, it's a pleasure to be here. So just before I just start, so I'm also together with Isabella, coordinator of this conference. So I'd like to express my gratitude to Demo Investments for all the support for this conference. And thank you everyone for being here. I would like to, so you see my slides, right? Let me put it in full mode. So this talk actually has many co-authors. The papers that I'm presenting, I just put myself here because there are so many. The fact is that it should not be a talk just about one paper. I will present, this is a paper that was published already. There is the link there for anyone that wants, but I will talk very briefly about it. The main part of the paper will be, which is the title in the program. It's about portfolio selection using quantile preference. The idea came from the first paper, and I'm going to also to present some results in this other paper. The working paper is still not available for circulation, and maybe the title will change, but the idea is to present some properties of quantiles that may be used for people working in quantiles, especially as doing this work in quantiles, found the necessity of proving some properties that we didn't find in the literature, and then this is the idea of this paper. I'm going to present some results there as well. But before, let me try to illustrate, to tell you what's the basic problem that you're looking at. So you have the basic economic problem of maximize the expected utility of an asset that's a random variable that you can buy, that's in some set. And what the expected utility does, as we know, if you take this as well, sorry about my line is not so good, but well, we'll go with that. So if you take a distribution of u of x here, what the expected utility does is taking the second equivalent, and then you try, of course, you have many x's in your budget set or in your set of choice, and you choose the one that gives you the highest expected value. So this is the economic problem that we have been studying for years and years. What we are looking at is a problem where you have essentially the same distribution, but you can look at different second equivalents. As tau comes from a small number to a high number, high tau, you can go over the support of u of x. Actually, I'm going to comment in a moment that u is not so important in this case, but the main idea here, what I want to convey is that I'm trying to look parallels of, instead of using expectation, using quantiles. This is the main basic idea behind it, and we are trying to look at then the problems where the function that you are trying to maximize is not based on expectation, but based on a quantile, which is in some sense it gives also certain equivalent of the problem. And once you understand, and I hope that it's very clear what we are looking at and the kind of problems that you're looking at. So for instance, I'm going to comment in a moment, but The X here would be a portfolio, right? We combine a number of assets, invest different weights in different assets, and then you come up with a portfolio that will be X, and this is the thing that you want to maximize. One way, the usual way of looking at it is to maximize the expectation of this portfolio. And you can take the mean variance approach, for instance. It can be written this way. But what we are looking at is, instead of maximize the expectation, you maximize the quantile. And then you can ask, okay, so why should you care about it? Of course, we know that there are applications in finance already with value at risk. That's just a quantile. And in some sense, some of the things that I'm going to talk about may be useful for other risk measures, but I'm very focused on quantiles. Well, this is one application. There is another. In some applications, especially with respect to risk, you can use quantiles. A couple of days ago, Marco Vallaneda presented a paper talking about the core, and he mentioned a function, a maximization function, a target function that's based on a quantile as well. So there you go. We have other applications. I have all the inspiring application here that comes from the mining industries and oil industries, which is when they look at the proportion of how much oil they expect to get in a well. They look at these numbers, which are just the quantiles, right? This is the 10% quantile, 50%, 9%, and actually the reverse. The P90 is the 10% quantile. And then they try to look at combinations of the wells to see what they expect to extract in terms of well. So these are some applications that you can look at. There was, in this paper that we wrote, that we published, the paper, the model that we got is a dynamic programming model. So as you know, dynamic programming is something that's very important for economics, macroeconomics. And what you did was to do this problem and develop all the theory where the quantile substitutes the expectation. The main motivation for doing this exercise was to provide a micro foundation for quantile regression. So my co-author, Antônio Galvão, who is in University of Arizona, is a econometrician and works with quantile regression. He had this idea of trying to go after a foundation for quantile regression, and then we came up with this model, developed the theory to kind of provide this foundation. However, as we have done this and realized after just the fact, as it turns out that's very common in research, right? We realized that this model is very useful to disentangle elasticity of interval substitution from risk aversion. This is a model that this is a separation that can be done in our model, in the quantile model, but not in the expected utility model. In the expected utility model, these two parameters are kind of interlinked, and you cannot separate. And actually, after that, we wrote another paper exploring this benefit. We also have other papers. This is a project that got us very excited. We actually went into experiments and we did an experiment with another co-author that expert in this field, and found that many people actually seem to maximize quantiles instead of expected utility, which is kind of, for me at least, was very surprising, but it was something that we found, and it seems very robust. Well, this is some of the motivation, that the more economic motivation. As Jim said, I was in US for a long time and in economic departments there. So this most of our motivation is economic motivations. But so let's get to some preliminaries. Fortunately, Andrea already defined the quantile, so I don't need to go over it. Let's just a comment that I made about the utility function comes exactly from this property here. If you have a monotonic transformation, you can take it out from the quantile. Of course, this is not true for expected utility unless the psi there is linear. And with this property, so in some sense it's stronger than the expectation, you can define a preference. So the usual preference is the expectation, right? I want to make this um, parallel very vivid in your mind because it's important for what you do. So this is the standard expected utility preference. We're substituting it by a quantile where the quantile goes in the place of the expectation. And because of this property, you can take U out of it. And if U is just monotonic in R, so of course these are the conditions, then what you want to see is the quantile. As you know, one important thing from expected utility is that the U is responsible for studying risk aversion in expected utility models. In this case, it's not because U doesn't make a role. So you may ask, what's the risk attitude in this model? And the risk attitude is just tau. So it's a in-dimensional parameter. It's some sense simpler than have a whole function to study. And I can explain why this is the case with this property. That's actually it's a very interesting property. This quantile preserving spread. So if you have two variables here, x is a variable that's more concentrated around this point, as you can see, right? So it's more points here, more probability here. So it's very concentrated around more or less these values. And y is a stretch of x, right? So it has, there are some probability that has a low value and also some probability that has y value. The interesting point about these two random values is that they have the same quantile tau bar. And so we can say that y then is it's a quantile preserving, the tau quantile, the tau bar in this case, tau bar quantile preserving spread of x, because it stretches s, is more risky than x, but preserves the quantile. So if you look at the behavior of a quantile maximizer in for these two assets, if tau, the quantile that you maximize is low, like this one, you have here y, and you have the quantile of x here. So the quantile of x is small. In this case, the smaller taus prefer x, which is the more concentrated, less risky asset, and the high tau prefers y, because this is the quantile of y and this is the quantile of x. So the high taus prefer the more risky asset y. So in some sense, this is actually this is a sense introduced by Mansky in 1988, where you can see the risk attitude in the quantile model just by tau. So the low tau are kind of risk averse individuals that prefer the more concentrated variable, the less risky variable, and high tau prefer the more risky asset. Okay, so this is just the preliminary. Let me go into the details. I think that I spent too much time, but let's go fast here. I'm going to describe just a set of our results and concentrate in these two assets. So your problem is to find the weights to put in two assets, x and y. For this part here, we're going to use a very, I mean, it's kind of an assumption that you have a density function that is C1, and it's over these intervals. However, x bar and y bar, this can be infinite, okay? So it's not really a compact interval. So the first result, it says the following. If you have the same low end of the two intervals, then you have a threshold over which, below it, you can actually choose an interior solution. When you maximize wx plus 1 minus wy, you take a y that's strictly between 0 and 1. An example, for instance, is if you have, you see here that the same low interval, and I think that this picture tries to help you. So if you look at the 0, 1, this straight line here is the uniform density. As you combine different w's, this is 0, 0 0.1, 0 0.5, and then you go, you have different CDFs for the variable SW, which is the combination of these two. So you see the one that is here, it's the W equals 0.5. So if you have a low tau, you get exactly this because it gives the higher quantile. However, if you are this kind of a tau maximizer, then you go for one of the other. So this is explained or illustrated here. This is the optimal choice. So the optimal choice for low tau, and actually the tau goes to 0.5 in this case, is to mix the two assets, and then you go for one or the other, in this case 0, 1, because they are identical. Which is interesting is that this diversification can hold even if you have stochastic dominance. So in this case here, X stochastically dominates, first order stochastically dominates Y, but you still contribute or to pick a combination of both for a small tau. There is another thing, and now the case where the difference between, so you don't have the first assumption where the first, the lower level of the interval is equal. So when it's not equal, what you can happen? Well, in some sense, the shorter or the response is that everything can happen, so at least in this case, if you have a condition here that X and Y, the lower end, are sufficiently different, then you do not diversify. So the idea is that you have here, let's see if I can draw this. Let's say X bar, lower bar. You see that this is the support of these two variables. X bar is above Y bar. So the idea is that you control the weight that is in this assured area here that I draw, which is related to this. Okay. So if you have a bound on the density function, then you can show, and if this bound, if this difference in the two bounds is sufficient large, then what happens is that there is no diversification at all. But this is not the case if you don't have this bound, right? So you can have an example in this case here, where even though the variables do not begin in the same level, so they have different. So you think that maybe this, for low tau, this would be safer, but actually for this low tau guys, they actually diversify, right? So this is what this picture is showing. Well, and then we have other cases. I'm going to skip this. There is other theorem here that we have for high tau, so this is high. You remember that high tau is the guys that optimistic or risk lovers in some sense. So there is a risk lover. They don't hedge in some sense. This is the idea that they pick one or the other asset. And well, fortunately, I still have time to discuss some properties of quantiles. Let me go. This is a paper with Jorge Zubelli, Bruno Nunes, and Antônio Galvão. Bruno is a student of Zubelli, student of IMPA. That's very good. And we are discussing some of the properties of quantiles. The idea of this paper was exactly to try to get some properties for quantiles that we try to use in our theorems, in our analysis, and we found out that a lot of properties that hold for expectations do not hold for quantiles. For instance, you don't have linearity. So if you have a variable that is negative, then you cannot take out of the quantile as well. You can do with positive ones. Of course, there is a relation that this goes 1 minus tau, but anyway, the important thing is that this is different. And also, and this was an important problem for dynamic theory. The law of iterated expectation, so if you put expectations here, of course, this will go with equality, right? So if you put the expectation here for sigma isomers that are included one in another, then you have the law of iterated expectation, they are equal. And this simplifies a lot the analysis in dynamic problems. But we don't have this in quantiles, and this was a problem that we had to circumvent. So the idea is, what can we find in terms of mathematical properties that you can prove that useful for quantile and useful for applications? And so I'm going to present a couple of them. The first one is the Jensen inequality. I remember this, that's valid for expectations, right? For U concave. And we are able to show a similar result, at least for tau below half. We didn't find the result in the literature. This seems a simple one. It's a very intuitive and very straightforward to ask if the Jensen inequality holds for quantiles, but we didn't find this in the literature. Actually, we found just for tau equals half, I mean the median, but not overall. So we generalize this Jensen inequality for quantiles, and of course, a similar one happens for convex functions. Of the inequality goes in the reverse, but it has to be for the high taus. Okay, so it's not total generalization of inequality for the Jensen inequality, but at least for a restricted set of taus. This is the first result. There are a couple of other results that I will not have time to comment here, but we also proved some continuity results, convergence results, and in some sense, a lot of them, which is interesting, is that the convergence for quantiles seems to be easier than the convergence for expectations, which kind of, at least for me, was surprising. But a lot of problems that you have with integrability, at least when you focus, just as we are doing here for quantiles between 0 and 1 strictly, you don't have much problems with integrability, and a lot of convergence results hold quite naturally. Here, in some sense, easier than the expectations result. We also have, which is kind of interesting, and we didn't find in the literature at all, is a Fatou lemmas for quantiles. Again, we are looking at this relationship between quantiles and expectations, and looking at the properties that hold for expectations, see if they hold for quantiles. In this case, we have the Fatou lemma for quantiles. which is kind of very interesting, and it's powerful. As you know, Fatou lemmas, it's a powerful result, and for quantiles gives us some interesting results. So, for instance, implication of this is that if a function it's a sequence of variables converge almost surely to x, then the quantiles also converge in all points, okay, for all taus. So that's quite useful result as well. Remember that I said that in general you don't have, you cannot put the differentiability result inside the quantile. Of course, you can do this for expectations, provided that you have integrability conditions. But in general, in general, these equalities is false, and it's not that difficult to find the contact examples for that. However, and this is also the first result that we saw in the literature, if you take a function that, of course, it has to be differentiable to look at the derivative of it. If it's increasing, h is increasing in z, and d, which is the difference, it's like it has to, h has to be increasing and have increasing differences. If you have this property, then you can actually put the differential result inside. There are a couple of other variations of the result that will be in the paper as well. So then we go to conditional quantiles. We generalize the definition of conditional quantile. This function that is used here is a function, as you know, this inclination is tau, this inclination is tau minus 1. This is the whole tau. It's a real function. So you can define the conditional quantile in this way, and then you prove that you actually there are other equivalent ways of five. So in some sense, we are considering five different definitions that are all lead the same object. But it's useful because you can actually work with some of them are more convenient than the other. The important part is that these functions will be G measurable. So from these, we can generalize a lot of results or properties of quantiles that are known for the standard quantile, right? We generalize for the conditional quantile. So monotonicity, the fact that if y is independent of g, then it collapses. If x is g measurable, then it can be taken out of the quantile. The other property here that is known for the expectation of a g of x is the integral of g of the quantile of x in d tau. This is known. What we have done is to generalize this for the conditional properties. And there are other properties that are also known for quantiles in general, but we generalize for conditional quantiles. And this is another one that's kind of if you have this property, this kind of in the direction of the linearity. If the a and b are g measurable function, then you take the conditional here, then you can take out a and b. The interesting part is that the b has to be decomposed in two parts, on the negative, the positive, and the negative parts. And for this, you can also obtain, as the Jensen inequality that I showed before, the Fatou's lemma as well for conditional quantiles. And finally, and my time is over as well, I have also a result of functions, G functions. You can actually, under these assumptions, you can put the quantile inside the G function and everything works well. And I think that that's it. I'm going to stop here. Thank you.
Okay, thank you very much, Luciano. I don't see any questions from the audience just yet, although let me invite the audience to ask questions. But while we're waiting for questions from the audience, as usual, I'm really interested in applications of all this stuff. So it's all these, it seems like you've done a lot on the mathematical properties. I'm wondering in practice, if you choose to maximize, let's say, the 90th percentile or something, what does it do to your portfolio when you use it for portfolio selection?
Well, yeah. So what we have found is that if once you go for high quantiles, the 90% that you mentioned, you become very risk lover. So, so in some sense, most of the cases and all the results that kind of we looked at is that it seems to be the case that after a certain threshold, does not need to be half, but after a certain threshold, for high enough quantile, you're going to pick the most optimistic one. So you look just at the most prospective, the most the ones that give you the most at that level of probability, and then you go for it. So you become a very risky lover. The idea of losing, I mean, the value at risk, it goes in the other direction, right? It goes in to look at the small quantiles to kind of prevent risk. But you can go either way, which is interesting that even with just one parameter between 0 and 1, you can have the whole range of attitudes toward risk.
If I may add, since I'm co-author in the paper, in the second paper he was talking about, can I add one part to the answer from Luciano? I think what Jim was alluding to is the fact that how can we use, for example, these extra results we have concerning the sigma algebras and I think there the fact that we are now able to do lots of these properties with a priori information concerning the sigma algebra, then we can adapt many results on conditional optimization, conditional, or for example, on let's say dynamics of the process, so that we can then iteratively get decisions according to the flow of information. So that's I think the practical application here, Jim, is to have the possibility of using the flow of information given by a filtration, for example, in order to be able to do optimization.
Okay, here we also have another question from Sebastian Jaimongal. He's asking, is there some connection with distortion risk measures?
So do you want to answer this, Josh? You know better risk measures than myself.
Well, we haven't looked into that yet, but I think that the moment we start doing conditional information, like conditional quantiles, then we can set up the stage for distortion risk measures and distorting risk measures. So I thank Sebastian for this interesting comment.
Yeah, I would add just this, that we suspected that these conditional results can be generalized to risk measures, but I mean, we didn't explore this yet, but yeah, probably.
It sounds like a real new branch of portfolio selection going on here, to me anyway. So thanks very much for a very nice talk, Luciano.